Chapter 4 of the Cambridge A-Level Physics Theory, Forces, Vectors and Moments. In this chapter we will learn about these topics. So after we finish this, now the topics are here on this side: combining forces, components of vectors, center of gravity, turning effect of force, torque of a couple, and we have the summary and end of chapter question. So let's see what are the learning outcomes. You should be able to add two or more coplanar forces. Coplanar forces are forces in the same plane. A plane is an imaginary surface. Resolve a force into perpendicular components. Now if you are given a force, you have to find the components of that force. I will show you over here. See, component of a vector. If a vector is like this, you should be able to resolve it this way and then that way. So let's say this is in the x-axis direction, this will be in the y-axis direction. The angle here is 90 degrees. So that's what we mean by this point. Resolve a force into perpendicular components. Define and apply the moment of a force and the torque of a couple. Moment is the turning effect of a force. So moment of a force is the turning effect of a force, and the torque of a couple. Now if I go over here, you can see torque of a couple. You should know what a couple is and what torque of a couple is. See, torque of a couple equals one of the forces into the perpendicular distance between the forces. For example, you see here a pair of forces like that in figure 4.25 is known as a couple. Figure 4.25 is this: you have one force this way and the other force this way. These two forces are anti-parallel. That means if both are in the same direction and equidistant, we say they are parallel and also in the same plane. So these two forces are in the same plane, but they are in opposite directions like this, and they are they have the distance. If you extend these lines, they are equidistant. This line and this line, their lines of actions are equidistant, and the directions of the forces are in opposite directions. So we say that these two forces are anti-parallel. This is what we call a couple. A pair of forces like that in figure 4.25 is known as a couple. A couple has a turning effect but does not cause an object to accelerate. So it tries to rotate this or turn this steering wheel in this case. To form a couple, the two forces must be equal in magnitude, parallel but opposite in direction, separated by a distance d. So you see, another key point is that they should be the same size. So these are the criteria to form a couple. Parallel but in opposite direction means anti-parallel. Okay, then torque of a couple is one of those forces into the perpendicular distance between them. In this case, it's 15 times this distance, which is 0.4. Okay, so let's go back to the learning outcomes. Define and apply the moment of a force and the torque of a couple. Apply the principle of moments. In the O-level class also you would have learned about the principle of moments. The principle of moments state that the sum of clockwise moments is equal to the sum of anti-clockwise moments. So if an object is in equilibrium, remember there are two conditions. The resultant force should be 0 and the resultant moment should be 0. If the resultant moment on an object is 0, it will not rotate. So for example, if it's a beam, the beam will be balanced if the resultant moment on it is 0, which means the sum of clockwise moments is equal to the sum of anti-clockwise moments. Then we can apply the principle of moments. State the conditions for a body to be in equilibrium. I told you just now that there are two conditions for equilibrium. I will show it to you here also. For an object to be in equilibrium, two conditions must be met at the same time. The resultant force acting on the object is 0 and the resultant moment is 0. Okay, so let's go back to the beginning and try to complete this chapter. Combining forces. Now if you look at this diagram, I have explained it, and I also have said what the moment of a force is. So let's go through. Now, from the name itself you can understand what we mean by combining forces. So it's like adding forces. You should recall that a vector quantity has both magnitude and direction. We learned about vector quantities and scalar quantities. Vector quantities have both a magnitude and a direction. Scalar quantities, whereas, have only a magnitude. An object may have two or more forces acting on it, and since these are vectors, we must use vector addition. Now if they are vectors, we can perform vector addition on them. And regarding vector addition, you can go through chapter 1. We can do vector addition to find their combined effect, that is their resultant. There are several forces acting on the car in figure 4.2. So you have this force, which is the normal contact force, also called the normal reaction force or reaction force. Why do we say normal force or normal contact force for this force? Normal means perpendicular. So always this is a contact force and it is perpendicular to the surface it is exerted from. Now this force is exerted actually at the wheels here and here, but they have drawn it like this to show you the resultant normal contact force. Okay, actually this normal contact force is acting on the wheels and perpendicular to the road because it is exerted by the road on the car. So the sum of the four normal contact forces acting at each wheel is drawn here with this arrow. Remember, the length of the arrow represents the size of the vector and the direction of the arrow represents the direction of the vector. The length of the arrow is proportional to the size of the vector. The direction of the arrow shows the direction of the vector. Remember what vectors are. Vectors have both a magnitude and a direction. Then this force is, we can say, the driving force, also called the engine thrust. This is the drag or the air resistance, or we can say these are all the frictional forces acting on the car. So it can be the air resistance plus the friction acting between the wheels, other frictional forces acting on the car, we can say. Then this is the weight force. The weight force is always acting from the center of gravity of the object and is pointing towards the center of the body which is exerting that gravitational force. Now in this case it is the earth, it is pointing towards the center of the earth. The weight is also called the gravitational force. So this we can say is the weight of the car or the gravitational force exerted by the car by the earth on the car. Four forces act on this car as it moves uphill. Okay, there are several forces acting on the car. Figure 4.2, as it struggles up the steep hill. They are, now I already explained this, the weight. The contact force is also called the normal contact force or normal reaction force, contact force. So you can see there are four names for this force. Normal contact force. Why do we say normal contact force? Normal, it's because it is perpendicular to the surface it is exerted from. So normal means at 90 degrees or perpendicular. So always this force is perpendicular to the surface it is exerted from. Then normal contact force. Now why do we say contact? Because there has to be contact between the two bodies for this force to be exerted. So normal contact force. In short, we say contact force, and also we say normal force. Then we also say normal reaction force or reaction force. Now why is it called normal reaction force? Because it's a Newton's third law pair. Now when the road exerts a force on the car tire, the car tire exerts an equal and oppositely directed force on the road. So for one to exist, the other should be there. Therefore it's a Newton's third law pair. Now if you watch one of the previous videos that I uploaded about the Newton's laws, especially I created a separate video explaining the Newton's third law. So once you watch that, you will know everything you need to know about Newton's third law. Remember, there are about 6 or 7 criteria for a pair of forces to be Newton's third law pairs. It should be the same size, acting on different bodies, have the same line of action, same size, act at the same time, have the same line of action, so there I have created a video, so you can watch that for all the details. And remember, they should also be the same type of force. Okay, if we knew the magnitude and direction of each of the forces, we could work out their combined effect on the car. Will it accelerate up the hill or will it slide backwards down the hill? So once we know the resultant force, we can have an idea what will happen to it eventually if that force is the net force on this vehicle. Four forces acting on this car as it moves uphill. The combined effect of several forces is known as the resultant force. The resultant force is also called the net force. So if we can combine all these forces and get the net force, that is the resultant force. To see how to work out the resultant of two or more forces, we start with a relatively simple example. Two forces in a straight line, that is very simple. When you have two forces, they are acting, let's say they are acting in one dimension. So if it is in a straight line, they are in one dimension. So we have to simply add or subtract. Okay, now if I try to show you what is happening. If it is in one dimension, it's along a line. You have to know that. If it is in two dimensions, it's in a plane. So if it's in one dimension, the two forces are either to the right, in other words, it's in the same direction. So let's say this is a 7 Newton force, and then we have another force like this. It's having the same line of action. Okay, let's say this is 4 Newton force. Okay, so the resultant of this is the sum of both of these arrows. So remember, I told you previously the length of the arrow represents the size of the vector. So if we have, let's say, this thing for this much long, 11 newtons. Okay, so these two add up, they are in the same direction. Now if these two forces are in opposite directions, let's say the 4 Newton force, okay, I will draw the 7 Newton force like that, and let's say the 4 Newton force now is this way. Okay, just thicken this part a bit. Okay, 4 newtons. Then you can see they're acting in opposite directions. So 7 minus 4 will give you the resultant force. So say it will be, I think, like this, right? 3 newtons. Okay, now these are forces acting in one dimension, meaning they are acting on a straight line. Then we can have forces acting in two dimensions. All right, let's see the next one. Okay, so that's in one dimension. Now the example here also shows that. And remember what we found here is the resultant. Here the resultant is 11 newtons. Here the resultant is 3 newtons. Let's add that also. Okay, so the resultant of these two forces is 11 newtons. The resultant of these two forces, again in opposite directions, is 3 newtons. And you can see another example here. The resultant force is equal to the weight minus the drag force. The weight is 1 newton, the drag force is 0.2 newtons. Therefore the net force is vertically downwards because this force is bigger than this, and that is 0.8 newtons. Let's see. When adding two or more forces which are in a straight line, we have to take account of their directions. So the maximum force that we can get from two forces is when they are in the same direction, and the minimum force that we can get from two different forces is when they are in opposite directions. This will give, but if they are at an angle, if these two forces are at an angle which is neither in the same direction nor in opposite directions, then the force will be anywhere from 3 newtons to 11 newtons. Okay, so you can see I added this to the diagram. Now if the two forces are in the same direction, that is in one dimension, then you get the maximum force. If the two forces are in again in one dimension but in opposite directions, you get the minimum force that can be produced by these two forces acting on a certain body. All the other possible resultant forces produced by these two forces are between 11 newtons and 3 newtons, which is when the angle between them is, over here you can see the angle between them is 0 degrees. Here the angle between them is 180 degrees. So we can even draw that over here. So you can see the angle between these two forces is 180 degrees. and the angle here between these two forces is 0 degrees. Now if the two forces are at any angle between 0 and 180 degrees, then they are in two dimensions. That means they are in a plane. Here they are on a line. Here also they are on a line. If the angle between them is anywhere between 0 and 180, that means let's say one of the forces is like that, the other force would be like this, and you can see they are in a plane. They are on an imaginary surface, you can remember. So here we can say the angle theta is between 0 and 180 degrees. Zero and 180 degrees. Because if it's 0 degrees, then this is the case. If it's 180 degrees, then this is the case. So they will be in one dimension if the angle between the two forces are 0 or 180 degrees. Now here 4 newtons, 7 newtons. This is in two dimensions. Let's go back. Two forces at right angles. Now here you can see we can draw it like this, or we can also draw it like this. As long as we have the same length and the same direction, the two forces are can be shifted from one position to another position, and like this, and the forces are not unchanged. So if the forces are the same size, which is represented by the length, and the same direction, which is represented by the direction of the arrow, if there are two forces like that, then those two forces are equal. So if you have an arrow equal to this arrow and in the same direction, that means it's another 6 Newton force. Similarly, if you have an arrow which is equal in magnitude to this to represent a vector and in the same direction, that means that force is also, that vector is also 8 newtons. That force is also 8 newtons. So we can shift it like this. Now here also this and this, they are in proportion. Now here the scale may be, for example, 1 centimeter is 6 newtons. Here it would be like 3 centimeters equal to 6 newtons. So here may be like 2 centimeters. Then here also you have to take the same scale that you took when you got this 6 Newton force. So the direction is unchanged. The size of the vector is also unchanged. That means if two vectors are equal, if they have the same magnitude and direction. Now we can place it like this, with the tip of one arrow connecting the tail of the other arrow, like this. So here is the head or the tip of one vector, it is connecting to the tail of the other vector. Then the resultant is the arrow connecting the gap between them. Now here you can see it's only this force and this force. This was not there. So there is a gap here. Okay, you can connect that gap using another arrow, which is actually the resultant. So remember, when you connect the tip of one vector to the tail of the other vector, they are in the same either clockwise or anti-clockwise direction. Now here you can see these two are in the clockwise direction. Then the resultant will be in the anti-clockwise direction. Okay, so I think I have some explanation. Okay, so you can see these are in two dimensions, and you can see the method it is, you can do it also is shown. Now if it's just two vectors acting, we can, and if they are perpendicular like this, the angle here meaning is 90 degrees, here is 90 degrees, here also it's 90 degrees, then we can find the resultant using the Pythagoras theorem. We can also find the angle here using trigonometry. We can use tan to find the angle, and that is what is explained here. You can use Pythagoras theorem to find the resultant of these two forces, and you can find trigonometry to find the angle between these two forces. Okay, so the resultant force is 10 newtons. So the resultant of this and this, it should be in between these two, right? You can see using common sense, this force is pulling it this way, there is another force pulling it this way. So the resultant or the net force should be in this direction, and you can see that is the direction. So the resultant force is in this direction at an angle of theta degrees to the horizontal. So that theta we can find using trigonometry, 53 degrees below the horizontal. This is a reasonable answer. The weight is pulling the shuttlecock downwards and the wind is pushing it to the right. So this force is due to the weight. This force is due to the wind. The angle is greater than 45 degrees because the downward force is greater than the horizontal force. Okay. So if this force is greater, that means the resultant force will be more towards the force which is greater. Now this force is greater than this, therefore this resultant force will be closer to this 8 Newton force. If you draw scale drawing, be careful to state the scale used. Draw a large scale diagram to reduce the uncertainty. A common mistake students make is they draw these diagrams too small. So when you're drawing a diagram, make sure it's large enough. So state the scale used and draw a large diagram to reduce the uncertainty. So let's say you can take a scale, maybe 1 Newton is 1 centimeter, depending on the size or space that is there also. Then this will be 6 centimeters, this will be 8 centimeters. Okay, so this is the case with 2 forces. Now you can do something like that even with 3 forces. You do the same thing. Join the tip of one arrow to the tail of the other arrow with all the arrows representing forces that are given. Then if there is a gap, that gap is filled by the resultant force. So in this case, you can see when you join this and this, there's a gap between this point and this point. So you connect that, and that line is opposite to the clockwise or anti-clockwise direction that these forces form. The resultant will be in the opposite direction, to the clockwise or anti-clockwise direction, and the length of the resultant will be giving you the size of the force. So the resultant force. And if you draw it to scale, otherwise you can do it like this by calculation. Now if you draw scale drawing and do this, you should also get the same answer if you do it accurately. Okay, so how do we do this? Now there are 3 forces. Again, do the same thing. Join the tip of one arrow or the head of one arrow to the tail of the other arrow. Now this is the push of the wind, the force representing the push of the wind. You draw it like this. Then this weight is, always vertically downward, so we draw it like this. See, tip of one arrow joining the tail of the other. Then we have tension in thread this way. Okay, that way. So here there is no gap. They all join each other without creating a gap. Now here there are only 2 forces, and obviously there should be a gap. Now even with 3 or 4 or 5, there can be a gap. Now if there is a gap, that means there is a resultant force. If there is no gap, if the polygon is closed, now a 3-sided polygon is a triangle in this case. If it is closed, that means there is no resultant force. Okay. If it is open, that means there is a resultant force. The length of the line joining that gap, like this, will be the size of the resultant. But remember, it should, now in this case, if there was a resultant, let's say there's a gap like here. Now you can see this, this and this, they are in the same clockwise direction. Then the resultant will be joining like that in the anti-clockwise direction if there was a gap here, for example. Now in this case, all the forces will add up to 0. So there is no resultant here. Okay. Now this is one of the conditions for equilibrium. If the resultant force is 0 and if the resultant moment is 0, then the object is in equilibrium. So this fulfills one condition for equilibrium. The spider should either be traveling with constant velocity or be stationary. If its resultant force is 0. You have learned this when you learned Newton's laws. Again, if you are not familiar with the Newton's laws of motion, you just go through the video that I created about the Newton's laws of motion. You will understand this. These are Newton's laws of motion. Okay, so what I explained just now is what is explained here about that closed polygon or closed triangle in this case. Why closed triangle? Because there are only 3 forces and the spider is in equilibrium. R is used for resultant force here, and you can see this is a triangle of forces. It forms a triangle. So remember, there are two ways to do this. One is by calculation like this, the other one is by scale drawing. Usually in your exam papers, paper 1, third or fourth question is usually on vectors. Now if you go through the videos that I created about the solving the papers, you can see that in paper 1's, like I think third, fourth question will be about vectors. If you go through that, you will understand that I've explained in detail these kinds of questions where you join the vectors by connecting the head of one vector to the tail of the other vector and then finding the resultant. You can also do this by scale drawing. So watch those past paper videos which are on vectors. And there is another videos that I've created just on these separate videos, just on these vector questions that students had difficulty with. So I picked those questions. I found them to be quite good questions, and it is in the classified past paper questions, I think. Okay, questions by topic playlist. If you go to that, you can watch those videos. It's not only for vectors, even for other topics like waves, superposition, which is a topic about waves. So what are these forces? One is push of wind, one is tension in the thread. Tension always points away from the object. Weight always points towards the center of the earth. Okay, so the next topic under this is components of a vector. Now we went through combining forces, and here we have component of a vector. That is the next topic, and I have created the diagram. Now you might wonder how you get this and this, and that's why I drew the lamp here. So let's say you have a force, a certain force like this. If you want to get its components, that means you have to resolve it parallel and perpendicular to the parallel direction, and that is, I think, what was here. Resolve a force into perpendicular components. So let's say we have this force, and let's say this is the x-axis direction, okay, or the horizontal direction. Then perpendicular to the x-axis direction, you have the y-axis. So remember, the angle between this arrow and this arrow are 90 degrees. So if you have a force like this, if you take the component of that force this way, then you take the component of this force the other way. Okay, and let's say you have a light bulb here, you have this arrow here. Then if the light bulb is vertically above this arrow, then it will cast a shadow like this right below this arrow. Okay, that shadow, we can say, is like the component of this force in this direction. Similarly, you can have a light here, and you point this light this way. Then let's say this is an arrow, solid arrow. Then it will create a shadow here. Let's say there's a screen here, it will create all a wall here, white wall. Okay, so this is a horizontal line. Okay, you point this so that the shadow is this is pointed horizontally. Okay, light source, so the shadow doesn't go up, it goes like this, horizontal, and then it casts the shadow. Now this is the y component. Okay, so that's what we mean by this. Now if you know this angle, f cosine theta will give you the component, f sine theta will give you this. So you can think of this triangle and the angle here. That's what I've drawn here. Okay, so this is the force F. Let's say this angle here is theta, this side is y, this side is x, so y, x. Then sine theta is opposite over adjacent. Opposite over hypotenuse, sine, opposite over hypotenuse. Yes, so that's what I wrote here. Then this side, now why did I write y and x? Because this direction is the x-axis, this direction is the y-axis. Okay, then cosine theta is adjacent over hypotenuse, x over f. So y equals f sine theta, x equals f cosine theta. So that's how you find the component in the vertical direction or y-axis direction and the component of the force in the x-axis direction. Okay, so that's about component of a vector. And there are questions where you have to resolve forces. It's there in past exam papers as well. And in questions like this also, you will have to resolve the forces. So again you can see these are forces acting in the same plane. So we can say these are forces acting in 2 dimensions, like what I have here. Now even here, when we resolve, we are getting the x-axis direction and the y-axis direction. So x and y-axis are in, again, an imaginary plane in 2 dimensions. If you have x, y and z axis, that's in a region, in a 3 dimension. Okay, so here forces acting in 2 dimensions, that is in a plane. A plane is an imaginary surface. Here we saw it in 1 dimensions. Now if you want, you can even do in 3 dimensions, but at this level we will not learn about 3 dimensions. If you go to university or if you take further mathematics, you will have forces or vectors in 3 dimensions, in the x-axis, in the direction, y-axis direction, and also in the z-axis direction. So far we are learning in 1 dimension, that is along the x-axis, for example. Then in 2 dimensions, that is in the xy region, xy plane, and then those two. So if you take higher levels, you will have xy z axis also. So that means you will have vectors in the xyz region. So you have the x coordinate, y coordinate, and also a z coordinate in that case. But here we won't have z axis direction, we will have only xy region, xy plane. Okay, so here you have this force and this force, they are in the same plane, same imaginary surface, you can say. You can see at once from the diagram that the forces cannot be balanced, because this force is this way, this is this way. They are not in opposite directions, they are not the same size, and there are only 2 forces. So that means this force is pointing down, so this will try to pull this way. That's why this will roll downwards. So we can find the component of this force, like what we did here. Okay, so how do we find the component? We can take W cosine of this angle here, which is 90 minus this angle. Now if you extend this arrow, the line of action, you shouldn't extend the arrow because the length of the arrow represents the size of the vector. But if you draw a dashed line along this arrow W, that is the line of action of this weight force. So if we extend that, the angle here will be 90 degrees. Then you have a right angle triangle, so that means this angle plus this angle here should be 90. So that means 90 minus this will give you this angle. So this angle is 90 minus theta. Okay, and remember what we did here. Okay, so what you can understand is that you have this force, and with this force you can think that as the hypotenuse of the triangle that will be formed when you resolve the force in the horizontal and vertical directions. So over here, when you draw this force, then you can draw another triangle here. I think it's shown here. Let's see. Yeah, so we will do that now. Okay, so this is the case that we have. Okay, that is the weight force. Now I'm going to resolve it. Here you can see this angle here and this angle here are equal. Why? Because remember that normal contact force, it's always perpendicular. It is like this. So this, if you extend this line, it will be along that normal contact force. This angle is 90. Then this angle here is also 90. Okay, now here also, you know, the angle is 90 degrees. The angle here is 90 degrees. Okay, so this is 90, then this plus this is 90. So 90 minus this will give you this, and that's what we saw in the book. This is 90 minus theta. Now again, this whole thing is 90, so 90 minus this will give you theta. So that's why this angle here is equal to this angle here. Now what we will do is, you can see I have formed a triangle here. Remember, when you resolve either in the horizontal or vertical or x or y axis directions, this will be the hypotenuse of the triangle. So you can take this direction to be the x-axis, this direction to be the y-axis. So imagine it's the x and y-axis rotated. So this is x, this is y. Okay, so we are resolving parallel and perpendicular to that parallel direction. So this way and this way. Now this side, okay, if I draw a parallelogram, okay, like that, then what we will have is this side and this side, they are equal. Okay, this side and this side, they will be equal in that parallelogram. This side and this side will be equal. Okay, so what is this side? That will be W, see this is the weight, W sine theta. So this side will be W sine theta. Okay, so that is the component of this weight force in this direction. Okay, then in the perpendicular direction, that is this way, you can use trigonometry. Okay, I used trigonometry just now. Then if you look at this triangle, this side will be W cosine theta. Cosine theta, W cosine theta. And remember, W cosine theta should be equal to n. Why is it equal to n? Because there is no motion in the vertical direction, in the perpendicular direction to this surface. So n equals W cosine theta. Or you can also use Newton's second law and show this. Newton's second law in this direction, okay, perpendicular to the surface, in that direction. So the Newton's second law, F is always a net force, so I can use the Greek letter sigma. By the way, I have created a video explaining the Greek alphabet. You can go through that. The Greek alphabet is important because we are using a lot of Greek letters in physics. So this is a Greek letter, capital sigma. Then now here what do we have? We are taking this perpendicular to the surface direction as positive. So it will be then, there is no acceleration, no movement in this direction, so no acceleration. Then it will be n minus W cosine theta, n minus W cosine theta. Then that's how I get this. Okay, so this force is equal to the component of the weight this way. Now in this direction, if you use F equals ma, the Newton's second law, in that direction, if you use the Newton's second law, F equals ma, there is only one force, that is the component of the weight that way. So that is W sine theta. These are exam type questions that you can get, okay, where you have to resolve the forces and find the weight, for example, of this trolley. They might give you the angle, they might give you the acceleration, for example, equals ma. So this way there will be an acceleration because the trolley will move down that way. So let's see. Okay, so you can see that acceleration can be found now. How do we find that? Here we can see W equals mg, so we can say mg sine theta, but we also need to know the angle. Okay, so equals ma. We assume also there is no friction here. Then this m and this m, we can divide both sides by m. We get A equals g sine theta. A equals g sine theta. Okay. Okay, so that's what's we have here, see, g sine theta, and that's resolving g down the ramp. Now to help understand this better, there are some examples. Now here you can see the trolley. There are also a lot of videos you can watch about these kinds of experiments on the ramp. Okay, so this is the important one. I showed you all this. Okay, you can see here, this also I explained. Okay, let's go through an example to help you understand this better. A boy of mass 40 kilograms is on a water slide which slopes at 30 degrees to the horizontal. You can sketch a diagram like this. The frictional force up the slope is 120 newtons. So this F is 120 newtons. Because he's sliding down, so always the frictional forces are opposite to the direction of motion. Calculate the boy's acceleration down the slope. Take the acceleration of free fall g to be 9.81. So let's do this now. Now here you can see it's just like what we did here. Okay, the force that balances the normal contact force is W cosine theta. Alright, so the normal contact force will be equal to W sine theta. W cosine theta, this one. Okay, so the component of the force this way is this one. Weight is W sine theta down the slope. The component of the weight perpendicular to the slope is W cosine theta. W cosine theta. Okay, so that is that way. So remember, this is not another force, it's just a component of this force in that direction and also in that direction. And I have shown the working here. You can see W cosine theta is the normal contact force, and that angle is 30 degrees. So you can also take sine of this angle, okay, because cosine of this, and remember this angle and this angle, they are alternate angles. You can see here like that, alternate angle. So this angle here is also 90 minus theta. So if you want, you can use sine for this triangle. Then when you use sine, then this will be giving you the same thing, same answer. Okay, so let's see. It's better to actually extend this or draw the lines of actions, draw dashed lines along the lines of actions, and then show the working. It will be easier for you to understand. Okay, first thing is sketch a diagram, then you can draw the lines of actions of the forces and resolve the forces in the directions down the plane and perpendicular to the plane. Okay, so the boy's weight is 40 into 9.81, 392 this way. Frictional force up the slope is the force F, and they have given that 120 newtons. The contact force N, and that is always perpendicular to the surface it is exerted from, is if it's a normal contact force. Okay, so now we can find it. Component W down the slope is W, I showed that, down the slope, W sine theta. Alright, so remember this is W sine theta. So we have that. So component down the slope is the weight, you can see W sine of this angle. Okay, and it's the same as cosine of that. So you can check, you can also use sine of this angle, which is equal to that angle there, which I showed. This angle and this angle are equal, so use this triangle. Otherwise you can use this angle, then it will be cosine 60. So that's what they are doing, they are using that angle there. Okay, so then you get that. Now component of F down the slope is, up the slope it's 120, down the slope means opposite direction, minus 120. Component of N down the slope is 0. You can see it's perpendicular, so if you take cosine, it's 0. Cosine of N, N cosine 90 is 0. Then the resultant force is the component of the weight down the slope minus the frictional force F. Okay, so 196 minus 120, which is 76. So the acceleration is, remember we can use F equals ma, that F is always a resultant force. So that is 76 divided by 40. 76 divided by 40, okay, which is 1.91. We are using F equals ma. So the boy's acceleration down the slope is 1.9 meters per second squared. We could have arrived at the same result by resolving vertically and horizontally. Now you can also resolve vertically and horizontally, but it will be complicated. So that's why we took the x and y axis directions tilted this way. Now if you take vertical direction as y axis, horizontal direction as x axis, then it will be complicated. So we do these kinds of questions by taking the components perpendicular to the slope and along the slope. But that would have led to two simultaneous equations, which we would then have to eliminate the unknown for force n. It often helps to resolve forces at 90 degrees to an unknown force. Okay, so that's the end of that. Next is about center of gravity, turning effect, and I think I've created another video on this, so check that out. Okay, so for more information about our online classes, you can check the links in the video description. There are several students who have gone from C to D, C and D students to A and A star students in a very short time, in about 1 to 2 months. To do that, you can purchase our complete online physics course. There are other courses also, and also you can check the student reviews and testimonials of how well our students did in a very short period of time. And I hope to see you all in an online class. The complete courses have everything you need to get an A grade for the exam. There are theory videos, there are notes, there are tutorials, solved tutorials. You can download the blank tutorials and watch the video solutions for those tutorials. There are solved past exam papers. Though there is an ample amount of content to help any student of any level go from maybe C or D grades to A and A star grades. And there are students who have also won world prizes from Cambridge, from Edexcel. So check the links in the video description. All the information you need is there. If you don't want to buy our complete course, you can also join our one-on-one sessions. But if you buy the complete course, you also get access to our one-on-one sessions. So for all that information, check the video description, like, comment, share, and I hope to see you all in the next video.